Hello everyone, I'm Gagana G, wearing USN 1V19MT005, a Department of Mechatronics, studying at Sri Venkateswara College of Engineering, Bengaluru. Now I'm gonna give a presentation on my project which I've taken in the year 2022 and 2023 with the topic name Design of Inverter Circuit for PV Power System under the guidance of Mr. Murugesh PD, Assistant Professor, Department of Electrical and Electronics Engineering. Now these are the contents I'm gonna cover with this presentation. One is abstract introduction, and then comes with literature review, problem statement, and the objectives of the project and methodology, implementation, circuit diagram, hardware and software used, and the application and the advantages, results, scope for the future work, and the project setup, conclusion, and the references. So here comes with the abstract. So here the main purpose of this project is to design the inverter for a PV power system with which gives increased efficiency, and also this recommended the architecture is achieved by coupling a typical boost converter with single phase full bridge DC to AC converter, and then we have lab prototype simulation and experimental findings are eventually produced, and they were agree with the theoretical analysis, and then we go for with some certain solar inverters inverter output AC voltage may be greater than its input DC voltage, and then we have few offered inverters just with the 5 active switches, so that switches can be driven synchronously by a variety of SPWM techniques, and then it's an integrated setup inverter for power generation without any transformer is designed. So let us come with some introduction about my project. So it's a stable, efficient operation of inverter. This depends on the basic of control mechanisms, and then this project is mainly about conversion of DC power to AC electricity, where we can use that in our daily life. And then these inverters are very essential components for renewable power systems, and it's a single stage DC to AC converter, and is its output voltage, and it's a single phase inverters as the most popular one in use, and then they must be capable of handling the PV system's voltage and the power ratings. So here come with some literature survey which we have referred for our completion of projects. So it's the first one is levelized cost of energy oriented modular string inverter design optimization for PV generation system using geometric programming. It was published in the year 2022, and the author as mentioned, and this is that it gives advantages of this paper is that it gives like clean and green energy source for free raw materials, and it's a versatile in nature, and it's a significant impact on the smart energy network, and it also helps us to have the reduced cost, and it has consist of like low maintenance, and it's kind of we may have cons also based on the particular paper. So it's an intermittency issues, and with additional investments, and also with the rest reliable power options. And the second paper named a multi-level transformer less photovoltaic inverter based real and reactive power injection for single phase systems. It was published in the year 2022, and here these are transformers inverters adapt with most technique to convert a DC to high frequency of AC, and the back DC and the finally standard frequency and AC, making the circuit board much complex. And here the transformer inverter synchronized battery DC with the AC input. And then coming up with the third paper, it's a modeling of power inverters used in PV systems. It was published in 2017, and here it's kind of conventional inverters where it's completely made up of transformerless inverters, so that it the whole prototype could be in later in weight, and it is more compact, and it's like compared to the conventional inverters, as it's one of the kind of architecture that would be used to boost up the inverters with the need of DC to DC converter bridge. And the fourth paper comes with a simulation study of small isolated power electronic converters for PV systems, and it was published in the year 2016. And here we have three main types of systems that can be designed and simulated. And it's quickly designed for power system, and it may estimate through hours, a month, by the month wise or the year wise for the energy production numbers, and was like for with the shading analysis. And it's a bifacial PV module mounted on the single tractors. Also, is challenge being faced on the designers. And comes with the last paper, designing a single stage inverter for photovoltaic system applications, was published in the 2013. And this paper helps us controlling the real and reactive power flow that is possible, and it's kind of less expensive to be purchased, and it's volatile in nature, and it can be connected or transmitted through very long distances, or like connecting with through two wires. And then the drawback of this inverter has to run to full output in order to maintain its change, and may suffer from overheating if there is not enough sun available. In the sense it can be boosted up when having that booster converter. So when we know that we may not get um, the consistency in the sun rays, so that we may there may be fluctuations in the input, so that we produce with the boost converter, so that it would reduce the ripples, so that we can get the particular and well designed input, so that we may get the proper output as consistency. And this inverter runs with the full output even there is no current coming, with potential causing damage to other appliances. Here we comes with the problem statements and objectives that our project would be done about. So here the problem statements are why the efficiency needed in an inverter, and how can inverters be made cost efficient, and can these inverters be used for power the loads, and is it fulfilling the growing demand for the energy. And the objectives for our project is the PV system converter topology requiring a high frequency transformer is very effective. And here it's basically about conversion of DC to AC electricity, and it's also maximizing the energy production with safety operations in the system, and its effective monitoring of electricity output, so that we could monitor how exactly and what exactly the output must be required by us. And it's also implementation of sinusoidal pulse width modulated based inverter. So here we comes with the methodology where we have PV panels and single phase voltage source inverter, where the driver circuit TLP250, and we have input DC voltage PWM generator that is consisting of like a big microcontroller with a value of 30F2010 controller. And we also have an RL road which acts as a filter, and AC grade it would be the final stage where it could be applicable, and then DC voltage that gives to the driver circuit. Here first, as we know that we would get the sun rays from the solar panels or the radiance, as we are considering with the hybrid material, so it just gives towards the single phase voltage source inverter, where we could find four switching devices that is used with the MOSFETs, where it is generated with the H bridge type. And then as we know the driver circuit, it produces the pulses for particular MOSFETs, and that would be basically controlled by this PWM generator with the controller DSPIC 30F2010 controller, where the input DC voltage is given to this particular PWM generator, where it controls, and it gives the pulses, PWM pulses with the 5 volts to driver circuits, where it takes the input from the DC voltage as 15 volts, and then from there it particularly gives the pulses to particular MOSFETs that is placed inside the single phase voltage source inverters, and that would go across with the RL load to just to filter the signal, so that we would get the pure AC grid, pure AC signals of about 12 volts. And this the circuit diagram, as I've told, that single phase rectifier is consisting of H-bridge type of MOSFETs, where here this is SPM inverter, where we have four switching devices that is made up of like MOSFET, and then we also have the diodes which would require for us to control the backflow. And then this is the LC filter, where it acts as the filtering of the like distorted signal, so that we would get the pure AC. And then the under one, we could see that this is the proposed technique, and this is a generator where it gives um, by comparing the conditions, and then it gives particular pulses to the gate drive circuits. From there it just directly goes to the inverters, where inverter system, where like if in case T1 2 to 3 T3 and T4, it would directly not all at once, based on the pulse that is given to a particular numbering of particular MOSFET, so that will be activated. So this is the implementation. The main components of this above diagram as follows, as I've already told. It's solar panels, inverter, driver circuits, SPWM wave generators, RL load, and input DC voltage. And according to the block diagram, it's just that main controller is PWM generator, which is powered by DC source, and it generates a pulse with modulated waves and feeds that same input to the driver circuits, so that the inverter module that is placed in H-bridge circuit takes the input from the panels, and driver circuit produces output at different cycles accordingly, as I've already explained. This is the simulation model that we have considered for our prototype. So based on this, we have like prepared our prototype. So here we have the irradiance that would be the artificial sun raises that would be given to the solar panels, and where all this will be uh, uh, like stored in these capacitors. As we could see, there will be fluctuations in the radiance or the solar rays that we would get from the sun. So as we have to have the consistency, and we have to send it without fluctuations, and to reduce the ripples that we have gotten from this rays, so we just store that in the capacitor to reduce the ripples, and that would be sent to this sensor, so that where the DC current sensor, where it would sense and produce the output through the controller. And then even this is this where this is a DC sensor that would give the um, output of this DC current, and where this DC voltage sensor, where it senses the voltage of particular place. And here it is the four MOSFETs. So it's like MOSFET 1, 4, 2, 3, and 4. And we have also this is the gate terminals, and we also know that diode is placed to just to ensure that there would be no backflow. And then after, as we know, as I have already told, that it's just have this H bridge kind of thing, where it in the positive half cycle by the controller. So by giving the pulses in the first half cycle, I mean the positive half cycle, where the MOSFET 1 and MOSFET 4 will be activated. So it would be present in the first half cycle, the positive half cycle, and in the second pulse when it is given, so where the MOSFET 2 and 3 will be activated. So the output will be formed in the negative half cycle. So it would give the a complete one sinusoidal wave. And then once this is done, so as we can see that there will be distortion, so it would just want to go across this filter. So here the AC sensor, current sensor is present, where it could sense the current of AC. And then here it's parallelly connected with the voltage sensor, where it would give the voltage AC voltage. And finally it would be connected to the grid or any other appliances that we use. So here this is the controller by which we are getting the particular output by as we could see that it would be the AC reference, and this would be voltage of the DC and voltage of the AC, and this is the current of an AC. As we have placed these sensors to sense and give the particular output based on the instructions, as and we could get all these outputs from these gate terminals of the each MOSFETs, and the output will be generated through this scope. And as we have run this like simulation by using the MATLAB Simulink. So we have got the efficiency across 96.23%, and the DC power is around 2295. And then this is how the simulation output looks like. So it is around maybe it can be controlled by according to our input, that is we are giving as DC voltage, and simultaneously we would get around 20 20 with the demanded RMS current, and this is the AC voltage that is crossed about 100, that might be around 140 to 150. And we can also see that AC current with sort of a distortion, uh, as these are the waveforms that we have generated for Simulink. So, and coming with hardware and software used. Hardware components are solar panels, driver circuit, MOSFET, DSP microcontroller, SPWM wave generator, diodes, DC voltage and jumper wires, and the software that we have used is MATLAB Simulink. As I've already explained about all these things in the previous methodology, so that I would clearly explain in the coming up with the prototype. And these are some specifications that we have mentioned with our hardwares that we have used. So I can guess that it's quite similar for everyone, which is also everyone we knew that, and you can go through this so that you can understand like what exactly we have just kept it here. And then coming up with this application advantages of our project work, the applications that would be, the inverters are mainly used as converters in a solar energy system, and your DC electricity, which is what a solar panel generates, is converted into AC electricity. And inverters are used as emergency backup where there is no power outage, and store excess power in the batteries. And the advantages would be, it's a cost effective and it would be like low maintenance. And then inverters maximizes the energy production, and it is also used to monitor, and it is also used to communicate with the utility grids, and that would help us to detect the faults, otherwise the solar panels or the solar system would be damaged. And it's energy independence, as we get it directly from the sun, so there is no need of giving extra any of the energies to the particular place. And it's an istatic gain, as you could see that it's istatic gain and provides a greater amount of energy output. The system with the low THD produces a clean stable electricity output that is less likely to cause interface with electronic devices or the equipments. So this is basically are the project setup, where we have with solar panels that is made up of like 10 watts, and then this is a trapping transformer, and this is the other transformer, and this is a voltage rectifier, and this is where the inverter system is placed with four MOSFETs, 1, 2, and 3, and 4. This is a capacitor, and no, this is the inductor, and the capacitor is placed right next to that, and this is a load resistance. This is the driver circuit, and this is where the PWM SPWM controller is set up, where it has, we could see that once we as this is, as we are demonstrating in demonstrating purpose, so we have built a prototype such as it would be the hybrid one. So we can also connect the solar panel where the in this place through the jumper wires and any other wiring connecting wires, and also we could give the um, input through the normal voltage. So we have giving this voltage over here as 230 volts. So this just cross verifies with this voltage regulator, and then this just goes, and we could see this DC output in this place, and then where it just goes inside this H bridge uh, inverter system, where MOSFET 1 and 4 will be activated in the first half cycle, in the positive half cycle, and this second 2 and 3 would be activated in the negative half cycle. And here we could find with uh, uh, with the distortion of the signals, where after once it is crossed, where crossing with the LC filter, where inductor is placed series to the H bridge, and capacitor is placed parallel to the H bridge. Once it goes across through it, we could find this pulsated pulse modulated output, and the output that we get from this pins or these terminals, it would go against to the load resistance, and we could get the pure AC signals over here. As we could see this controller, it would help to give the pulses to this driver circuit. By using these circuits, it would give the pulses to particular MOSFETs as per the requirements. It is based on the positive half cycle or the negative half cycles, and this tapping transformer helps to help give the signals to this driver circuit, so that it would give the particular pulses to the particular MOSFETs. Um, so this is the output that we have generated, and this is the DC waveform that we have got when through these terminals, as it is directly connected. So the output that input that we are giving here is 230 volts, and where it is coming over here, and it's just step down the transformer, and as we may get around 12 volts. And then this is the AC waveform with the distortion, where this could be found in this place where as it is connected directly to the gate pulses, and this driver circuit just gives the pulses to the gate pulses, sorry, gate signal, gate terminal. And this is the third inverter waveform, where this is taken from this terminal, where once all this pulses is given to particular MOSFETs, and its pulse and just this is like we have it kind of distortion, and then it is just passing through the and it is just passing through this RC filter, where we would get this pure RC filter, the output signals that is sent against this load resistance, so that we are getting the pure AC waveform at that particular terminal. And as we all know, there are certain um, what is that, what I can say, like more than more the research is going on, so that it would be beneficial for our daily life. So there would be scope and future work on every prototypes or any of the projects that we do. So as the further research should be carried out, so it's necessary in a particular a way that to determine the functionality of the circuit relations to applications of semiconductor devices that use silicon carbide, and these technologies can work at higher frequencies with very high efficiency, leading to decline the dimensions of passive components, and also with the recording loads and cost of the particular prototype. And the future work is aimed to design the hardware prototype of small signal phase inverter with the galvanic isolations as we require with the safety measures. And calculations of efficiency also can be done by using in the hardware prototype. And then the selective harmonic mitigation and elimination of kind of harmonics that we generate in the signals also must be controlled. And we could say that band reject filter can made use of to reduce this higher harmonics components in such output circuits. And coming up with the conclusions, we could say that, as we also mentioned with the scope of projects, SPWM inverter that is connected to grid for the PV systems have been suggested. So the modified version of PWM method is applied, and the results that is gained through voltage and the currents, as we have already seen. The upgraded VSI is able to achieve a greater voltage gain while the making use of lower shoot through duty ratios, and due to the absence of any dead time, it's also possible to achieve low levels of any output distortion. And due to these various contributing factors, its modified and improved inverter is now better suited for PV power systems or its NRAs. In conclusions and the end, that it's that like we have also done experiments using the MATLAB Simulink, and as we have already done, we have gained the particular suggested or any of the invert output, and it's delivered to predicted capabilities. And we have also published our project in the this 14th International Conference on Computing, Communication and Networking Technology. That is 2023 hybrid conference organized by IIT Delhi, and also with the International Interdisciplinary Humanitarian Conference for Sustainability, and it is basically organized by my college, Sri Venkateshwara College of Engineering, Bengaluru. So these are the reference paper that we have referred, and this is also referred for this literature survey, and it's already explained. So thank you.